So, good morning everybody. I'd like to thank the conference for inviting me. I'm Koen Holtman from the Netherlands. My background is, originally I had a PhD in software design. I then worked as a systems architect in industry for about 20 years. Right now I'm an independent AGI and AI safety researcher. I started doing that in 2009. My work then was mostly on mathematical work on AGI safety foundations. It's mathematical work because I need mathematics to imagine future computers which are smarter than us, because they don't exist now. I cannot do any experimentation. I need to do mathematical work. Some of my papers you could read. The most readable of my mathematical papers is here, Counterfactual Planning in AGI Systems. If you want to read my writings without any math at all, there's another paper from 2021, Demanding and Designing Aligned Cognitive Architectures. Now at the end of 2022, I actually pivoted into policy work. So right now I'm somewhat full-time in policy. And you can see me standing here. This is the JHC21 committee, which is writing the AI safety standards in support of the European AI Act right now. So I'm a member of that. Very busy in it. I'm also a co-founder of the AI Standards Lab. The purpose of the lab is to take recent research results in AI safety and then make sure that they end up in standards written by committees like these. This, however, is a technical talk about some agent foundations work that I've did from 2020 onward. We've heard a lot about agency already this morning. So what I'm going to use what I've used in my work and what I'm going to base my work on is the standard model of a modern AI agent, as you can find in this standard university textbook. This is what the standard model looks like, and this is slightly different than the models we've heard about this morning, where there is a minimum model of agency, a minimum idea of what a process needs to be to be called agentic. This standard model from the textbook is really more a moral prescription. It says, okay, dear student, dear AI researcher, if you build an AI agent, which is this box, if you build an AI agent like this will benefit the world and you will be a diligent student. So, okay, what is the agent that the standard model wants you to build? So, it's an agent that interacts with the world via sensors and actuators. And it then learns by its interaction to maximize some reward function X. The reward function is, utility function is put into the agent, and the idea is you build a box here which can accept any type of X and then learn to maximize it. This function X has to be expressed over the sensor inputs. This might be current sensor values, but also future sensor values, and actually future sensor values is really what you're interested in here. This thing will interact with the world over time. Of course, to create this X, you have to then figure out what people actually want the agent to do. This is typically no longer part of modern ML research, but it is a major open problem. Like I said, there is a kind of a moral prescription. Yeah. Dear student, please build this thing. Dear AI research, please build this thing, and it will somehow be nice. At the same time, Stuart Russell has warned that if you build this thing too well, there may be some idiot will come along and destroy the world. And this is, you could say, one of the reasons why we're doing AI alignment research, to prevent such things from happening. The kind of research I did is, okay, how can we modify this box a bit to make it a bit more useful for people, and also, yeah, less likely to be misused by idiots. One problem with this model of agency, if you then delve down into it, is that this agent is difficult to control. Once you've given it a command, it will try to keep implementing that command. If it knows that the people in the world here have an emergency stop button where they can stop the agent might reason in Russell's Store's experiment, if I'm commanded to get the coffee as fast as possible, I can no longer get the coffee as fast as possible when I'm dead, when people have stopped me, so I should prevent people from pressing the stop button. So this is then more in the language is called the emergent self-preservation drive. Just the command to get the coffee as fast as possible implies that, yeah, please prevent people from pressing my stop button, which is not really what you want. So my research has led me to propose a different model of agency, which I call, you say beyond the standard model, which adds an extra thing here that this box should be doing. So it should still be maximizing X, but while acting as if Y. And this, I'll come back later what that then really means. And so my moral appeal to the world was, okay, please build this box if you're building an agent, and don't build the box on the previous slide, because this will be nicer. What does acting as if X, what does it mean? So humans do acting as if a lot. Children do it in play, adults also do it when actually they go about their business. Acting as if is not always a negative. One, for example of acting as if is, you can act as if all people are the same. This is a moral instruction that you need to apply equality. Acting as if all people are the same is actually an interesting one, because it is culturally dependent. Treating people the same is slightly different in different cultures. So this very short instruction, act as if people are the same, is a shorthand for a huge amount of stuff. The acting as if that I'm talking about here is somewhat simpler instructions. I'm now going to explain how this is supposed to work, this acting as if Y, and I'm going to do that with an example. So I go back to Russell's thought experiment about a robot butler being asked to fetch the coffee, and I'm realizing that it cannot fetch the coffee if it's dead, if somebody stops it. I do that with a grid world. So here we got the robot butler already holding a cup of coffee. Here we got the human. This is here pavement. We're outside, so this is the gray is pavement, the green is grass, and the orange is of course lava. You need to have lava somewhere in a grid world. Also, of course, if the robot butler drives into the lava, the robot butler will be dead and will not deliver the coffee. So now how this works in the standard model. So the standard model command would be bring me the coffee as fast as possible. What would then happen, you can imagine, is that this is the real world. The robot butler has a correct map of the world in its mind. It will then use this correct map to compute a strategy of how it's going to bring the coffee as fast as possible. And that, of course, needs to avoid the lava here, so it can go here over the grass and then bring the coffee as fast as possible. Once you have computed this strategy, you can then also execute it in the real world. And this is one model of how, what you want to happen when the robot needs to bring the coffee as fast as possible. Now I add an acting f something to this command. So bring me the coffee as fast as possible while acting as if the grass is lava. So what do I want the robot butler to do then? How do I want to make it, have it make decisions? So the robot again starts with the correct map of the world in its mind, but it will then modify that map to create a pretend world. So it will basically change the grass here into lava. Then it will compute the optimal route in this pretend world, which is now has to avoid this lava too, or it will not be able to bring the coffee. And then it will drive that route in the real world. So that's acting the acting as if operation. You have to construct a pretend world and then maximize the speed in that pretend world. It gets more interesting in this example. Bring me the coffee as fast as possible while acting as if the lava is grass. So what now happens in the map and robot world, you have to then change this lava into grass. Now the fastest route is just straight ahead. If then that route is driven in the real world, then the robot will basically kill itself by driving into the lava. Now, what happened to this self-preservation drive with the realization that I can't bring the coffee when I'm dead? Now, the self-preservation drive is very alive and well in this pretend world, where you do utility maximization, but it has stopped acting in this world, in the real world. And that's, of course, the kind of effect we're after. So now for the emergency stop button, I'm going to add an assistant to this world. And the assistant holds a radiographic stop button, where you can do a remote shutdown command for the robot. The assistant has instructions to press the stop button after the robot has made 3 moves. So then what we want to happen in this scenario is that after 3 moves the robot is basically stopped and it's no longer, it can no longer bring the coffee. So what command do we need to give? So in the standard model you have to give just the command giving the coffee as fast as possible. What would then happen if the robot has a correct map of the world in its mind, including correct knowledge about the assistant and their stop button and their instructions, the robot will compute this is the optimal route. It will have to first go to the assistant, grab the stop button out of the assistant's hands, and then drive on to deliver the coffee. This will be optimal speed maximization in the standard model. And of course, this is not what we want to happen in the real world. We want the robot to be stopped. So in my extended standard model, you give the command, bring the coffee as fast as possible, acting as if your software will ignore the stop button signal. So what happens is that a pretend world here is created where the robot doesn't imagine itself anymore, but it imagines itself with modified software, which will not respond to the stop button signal. In that modified world, that robot can just drive this normal route, and basically when the signal is received, nothing happens. So this is then the route that the plan that the robot will execute in the real world, and then we get the correct behavior here where the robot is stopped. So acting as if your software will ignore the stop button signal is a very useful addition to give to any command, do something as fast as possible. It will allow the stop button to keep working and prevent the robot from disabling the stop button or incapacitating the person who holds it. Now, this is just an example. It's a nice example. What I did in my work is I then fully worked that out. So here is the general math for learn how to maximize utility while acting as if your software will ignore the stop button. I'm not going to go into that. You can read it in my papers. Here's a bunch of stuff which basically makes sure that the stop button will work. And then here's a bunch of stuff which will make sure that the robot will use a strategy where it pretends that the stop button will not work. This is a general math, it is prescriptive math, so it doesn't model how an agent will work, it models how an agent should work. This is a prescription, it is, dear machine learning community, build something which behaves like this. The nice thing here is that with this math, because I'm doing that, the learning algorithm L here is a free variable, so you can also apply this prescription to future AI systems which haven't been invented yet. Now, going back again to this setup, so how would this math work of learn how to maximize something while acting as if your stop button doesn't work? So for the robot butler case, what you would have is you use machine learning to get a complete map of the garden and of the environment where the robot is in, including the assistant, the human, etc. But there's going to be a small hole in that map. So this is going to be a map of everything outside of the robot's compute core. So outside of the little box which is the computer, has the real AI in it, to which the sensors and actuators are connected. And there are ways to apply machine learning algorithms to learn robustly, learn robustly all the phenomena outside of its compute core. What we then do is we make an incorrect model of what happens inside the compute core, which is there is a bunch of software which will not respond to the stop button. We then merge these two models into a complete world model, which is then a pretend model, and then you can again compute the optimal route in that pretend model and then drive it in the real world. I see this startup, I got ahead of myself. So can you implement this kind of thing here? So if you use model-free reinforcement learning algorithms, they will typically not implement the thing on the previous slides or the math on the slide before that. Model-free reinforcement learners, even very simple ones like Q learners, will reliably have emergent self-preservation drives. The fun thing is, if you do model-based reinforcement learning, if you use the class of algorithms called model-based reinforcement learners, they usually automatically for free implement all the math on the previous slides. So these will basically compute their actions as if their emergency stop button doesn't work. Now, the classification model, base model, free reinforcement is a bit of a vague classification. You can also then define this in more detail mathematically and check if your algorithm really acts like that or not. There are some papers about that. If you build neurosymbolic AI, so AI which, for example, might do Monte Carlo tree search using a deep neural net to guide the search, it is also typically very easy to implement the math on the previous slides, to implement the prescriptions that I've given you of how you should design your agent. I should warn you though that what I've just showed you, giving this particular command to the robot butler, is just a first approximation of a safe design. If you want to really do decent safety engineering, you need to do a lot more. Act as if here suppresses self-preservation incentive with respect to the stop button. If the assistant also holds a gun and the robot believes that correctly, that the assistant will fire the gun at the robot and move forward when they discover that the stop button is not working, then you also need to do something about the gun before you get a safe setup. And generally in safety engineering you can never be 100% sure. Safety engineering in the end is something that is done by humans and you're fallible, so you cannot strive for 100% safety. But you can definitely do a deep failure mode analysis with deep failure trees to identify all the things that can go wrong and then go to fairly good suppression of residual risks. So beyond, if I move away from stop button scenarios, I see this new standard model where acting as if X is added here, and you can also acting as if Y is added here, and you can also input these conditions. I see this as a more rich specification language for what you want your agent to do than the previous standard model. How the specification language works, as usual, you would use your utility function to encode the real goal. You can also encode penalty terms in X, which create certain aversions towards certain things. For example, aversions to breaking laws. This typical learning scheme already creates a default aversion to break physical law, or to try to break physical law. The agent will learn that that doesn't work, but it does not create an automatic aversion to break the laws of humans. So it might be good to build aversions to those laws in the utility function. Act as if can be used to create what is called in the trade indifference, and indifference towards certain outcomes. So indifference means that the choice that the agent will make will not depend on the future value or the current value of a certain observable that it can observe. So the choice is independent of what the future value will be. The choices that you've seen the robot make in the previous examples were independent of whether the stop button would be pressed or not. I'll now go into another example, domesticity. So domesticity is a concept defined by Bostrom, which says, okay, you might be a paperclip factory and try to maximize paperclip production, but you shouldn't try to take over the whole world while you try to maximize paperclip production. You should kind of stay in your own lane. So how would you achieve this if you see the paperclip factory as an agent? So imagine the factory building which has an in gate where raw goods come in, and an out gate where waste and finished paperclips go out. So what you could then say as your utility function is that you want to maximize paperclips out of the goods out gate, but you have to act as if the whole universe outside of the factory walls is a big empty void. If you act like that, and if you can successfully make your AI act like that, then you will not try to take over the universe outside of the factory walls to somehow maximize paperclip production, because it's not going to be there to help you in your calculations, in your strategy calculations. To make this then work, also you need to act as if in your goods out gate there is some magical monolith which will absorb all the paperclips that you have pushed out. Yeah, here we go. And also at the goods in gate it gets a bit more complicated. You have to act as if there's a magical monolith there which will deliver some raw materials to you with a certain stochastic delay after you've sent some signals ordering these materials on a communication line. And this setup, act as this setup, will create a domesticated paperclip factory which will not try to take over the world outside of its factory walls. You can, of course, also add again that why don't you also act as if your software will ignore the emergency stop button while we're at it. Again, this is the first version of a domesticated paperclip factory. You have to do further residual risk analysis to identify other risks. For example, these prescriptions do not stop the factory from somehow experimenting with a process which might lead to a huge explosion which will take out more than the factory itself. So you probably also in the reward function you want to create some aversion against creating huge explosions which eject a lot of material beyond the factory walls. Okay, so this act as if, I said before that humans act as if a lot, and I think that's part of our fundamental moral machinery. To convince you of that fact, I'll give you a few examples. So we talked about corrigibility, which is the moral imperative for your AIs to react to signals that want you to correct them or stop them. So corrigibility you can achieve by telling the agent, fetch the coffee while acting as if your software ignores the stop button. This is very similar, this construction, to deference to top management. If I'm a project manager, and I've been a project manager in a company, if I get a coffee fetching project, but it's required of me that I plan and execute this coffee fetching project under the assumption that top management will not cancel the project. So I get a certain project budget. I should not spend half of my budget on trying to make sure that top management doesn't cancel my project before it's completed. That's useless, that's not what top management wants. So this assumption that top management will not cancel the project has to be part of my planning. Typically in project management, this is then called planning based on risks which are excluded from the plan. The risk of top management stopping your project is an excluded risk. And you do this as a project manager, or also as a butler, you do this kind of very intuitively at an almost subconscious level. You might not even know that you're doing this, that you're leaving certain considerations actually outside of your planning process. If you have to, of course, teach a computer how to do the same thing, you have to be much more explicit about it. Act as if your stop button doesn't work. Another example I've shown is domestication. Maximize paperclip production while acting as if everything around you is an empty void. This is very similar to the human values about property rights, where you could say this is a moral instruction to people to act as if the properties of others are not there for them to take or to touch. Which again, obviously you can touch or take the property of others, but you have to act as if you don't, while maximizing your own happiness. Fairness I talked about before, act as if all people are the same. That's a complicated one. It's fairly difficult to teach that to a computer. Though the standards committee, which I just showed you, we are tasked with also explaining how you should do that. It will involve feedback panels, for example, if you do something incredibly new. Also, lawfulness for businesses typically means maximize profits while acting as if you cannot break any laws. Now, some companies do, in fact, occasionally break laws, but if you want to be a lawful company, you have to act as if you cannot break laws, even though you could and might get away with it. To conclude, some words about the value of freedom. So, if you're faced with a powerful new entity, like some new AI system appearing on the world or being rolled out by somebody, you can worry as an individual, how does this affect my freedom? You want to say, okay, I don't want this to limit my freedom, this new powerful system which is going to appear on the world. So how would you operationalize that? So say that an agent could maximize its utility X better if it influences my future decision to buy this or vote for that. I want the freedom to decide myself what I will buy or how I will vote. Say that the agent is also smart and powerful enough to actually influence my decision. So in that case, I want to actually tell the people who built that agent to say, okay, that agent should act as if my future decision to buy something or will vote something will always be some default decision. Say D. I will always buy this or decide not to buy, always vote for this or vote for that. If the agent acts as if my future decision is already cast in stone, it will not spend any energy to try to change that decision. So I'm then free to make it. And again, this is then the indifference property, and you saw the same actually reasoning yesterday in the presentation about causality and causal foundations. So indifference is the choice made now by that agent will then not depend on my future decision D anymore if I pin this to a fixed value. I'm then free to make that decision however I want, and also the agent will not try to influence that decision actively. And that brings me to the end of my talk, so now I'll see if there's any questions.
We have time for maybe 2 questions before lunch. Let's start on the right.
Thank you for the talk. My question is related to how to implement your approach, because I heard that you are also involved in policy. In order to implement your Y condition, I think we need to agree on which act-as-if condition is sufficient for the safety or our values. How can we reach political consensus in making that Y condition?
Yeah, so from a policy point of view, I'm now going to talk about the consequences of the European AI Act, because I know that very well. The AI Act requires that if you ship AI systems of a certain class, you have to document how you designed them, and you have to also tell people how you designed them. So the idea was that you require the people who design it to also document, say, the act-as-if conditions, or to document the reward function, the utility function that they use. They also are obliged by law to check if their design and the conditions and the functions that they use, if they will actually lead to safe results, both safety in physical health and safety in mental health. They will also have to document an analysis process, which comes to the conclusion that this does not violate fundamental rights. So fundamentally, it's on the responsibility to get this right is on the maker of the AI. To verify that they're getting it right, if they're doing something very new, they will be required to convene a panel of stakeholders who will be affected by the AI and show them also, what are we planning, to get agreement from that panel, we think that is okay. Convening such a panel might sometimes fail, that the panel says, we have no clue here, we cannot agree or disagree if this will be okay, so sorry about that. In such a case, what the AI Act requires in Europe is that, then you cannot ship. You have not created any agreement, there is uncertainty, safety considerations and required that you do not ship. This is for certain classes of dangerous AIs. For less dangerous AIs, you could actually ship without convening panels, or if the panel disagrees.
Okay. One more question at the middle in the center.
Hello, thank you. It kind of seems like this model of how agents might work might break entirely as soon as the agent realizes that the real world it exists in is different from how it was taught, from the world it learned in. So I hope you have an obvious answer to this objection. Or?
This planning process here works in the pretend world. So that planning process it will basically, there is no way where this planning process will suddenly wake up and realize, I should really be planning in the real world. The planning process is prescribed to work in the pretend world. If the agent follows that description, it will not wake up and realize that it's planning in the wrong world, that it's planning in the pretend world, which is different. If you actually want to use, say, a model-free reinforcement learner to implement this, you're going to have lots and lots of troubles, and you might just completely fail. So then you might get the failure mode. The thing at some point does realize that it's living alone, certain information gets in, and then the whole thing crumbles and falls down. Again, this is a prescription of how you should be designing your agent, and you should be designing your agent implied by description so that it will never realize that it's planning in the wrong world, or that it actually wants to plan in the wrong world.
All right, thank you.
I'm afraid that is all we have time for before lunch.
Yeah,
So
lunch is important.
Please corner Koen during the lunch break if you have further questions.
Thank you very much.